Okay, so far we've been ignoring air resistance for the most part, but it is a very real thing, and as a skydiver will tell you, it's kind of an important thing to understand, okay? So this is why we're talking about Part 4, terminal velocity. This also goes into the idea of balanced and unbalanced forces and how they affect acceleration, okay? So the first question really is what is terminal velocity, okay? Well, let's talk about this. Free fall on the Earth is not perfect, okay? If there was no air on the Earth, everything would fall or accelerate at negative 9.8 meters per second squared, right? It would keep getting faster and faster by the exact same amount, okay? It does that on the Moon. It does that on Mercury. It does that on Mars. Doesn't do it on Venus because that has a pretty thick atmosphere. But on all those rocky planets, that happens because there's really not much air there, okay? But on Earth, there's enough air that it'll slow, not necessarily slow things down, but it'll keep it from accelerating. So there is air resistance. Now, as you free fall and you wind up gaining speed, okay, the force of gravity pulling down on you stays the same. Your weight, the force of gravity on you stays the same no matter what, okay? So that force arrow in the diagram will be the same size the entire way. But remember, in the previous vodcast, we said that the force of air resistance changes with speed. And since you're increasing your velocity, you're getting faster and faster, the air resistance force will get bigger and bigger as you accelerate. So what happens is, at the beginning, it's very, very small. The air resistance force is very, very small, but the gravity force is really big, or big comparatively. And what happens is that, let's say the gravity force is this big and the air resistance force is this big. As you get faster and faster, they grow. Okay, the one grows, the air resistance force grows until finally it gets to the same size as the gravity force. So the point in free fall where the force of gravity is balanced out completely by the force of air resistance, that is terminal velocity. In other words, there's no acceleration because the forces are balanced. Okay? There's just as much going up as there is going down. That doesn't mean you're not moving. It just means that the forces are balanced and you're not accelerating. Your velocity doesn't change. So there's no acceleration and you can't move any faster. That is what terminal velocity is. It's when the force of gravity and the force of air resistance are balanced and you can't go any faster. Now, there is a little way. Okay, let's say you're falling this way, you know, kind of like a squirrel, you're kind of, okay. If you move forward and reduce your surface area and sort of point more like a pencil down, yeah, you could increase your terminal velocity, but eventually you would also reach a terminal velocity with that, okay? But that's neither here nor there. Let's just say you can't change your position. The point at which gravity pulling down is the same as air resistance pushing back. That is terminal velocity. Okay? So let's take a look at this in terms of pictures. Okay, so here we go. Here's what we got going on. We got this little skydiver here. Okay, and we'll call this time 0. 0 seconds. He just jumped out of the plane. Not even a second. Not barely any second ago. Like right as he's jumping off. Okay, and let's just say this is him 1 second later. He's further down toward the Earth. And let's say this is 2 seconds. Time is 2 seconds. He's now moved further than he did the last time because he's accelerating, right? And then 3 seconds later, he's moved even farther down toward the Earth because he's accelerating. His speed is increasing, right? Now, here's some things to think about, okay? If we draw forces on this guy, okay? Number one, there's going to be a force of gravity. Okay, so at time equals 0 seconds, he's got a force of gravity acting down. Okay, and he also has, well, actually no force of air resistance yet. Okay, but so what we can say right here is his velocity right now is 0 meters per second. This is like right as he jumps out. Okay, 0 meters per second, and at this point, his acceleration is negative 9.8 meters per second squared. This is how much he's speeding up, and this is his speed. Now, 1 second later, we got the force of gravity is exactly the same. Exactly the same, like, same force of gravity, except now he's got a little bit of velocity. 1 second later, he's probably moving about, well, 9.8 meters per second because it's 1 second later. Okay? However, because he's moving faster now, because he has a speed, he also has a force of air resistance, just a very small one, pushing up on him. Okay? Now what that does, okay, is that makes the net force, okay, the net force, the total force, the sum force, okay, different. See, up here at time equals 0, okay, the net force was just the force of gravity. That was the only force acting on him. 1 second later, he has the force of gravity, but now you subtract the force of air resistance. Okay? So let's say here maybe it was 200 newtons. Okay? Down here it might be closer to, I don't know, 180 newtons. Okay? I'm just making those numbers up. They have no real mathematical purpose. Okay? But what you see is that there's a smaller net force, and what that means, if there's a smaller force, there's a smaller acceleration. Now, let's just say, since it's very close, probably only -9 meters per second squared. So it's a smaller acceleration. Okay. So let's do 1 more second later. Okay. Again, he's got the same force of gravity, same size arrow, except now it's 2 seconds afterward, so his force of air resistance is a little bit bigger. Okay? Notice that the force of air resistance here is smaller than here, and that's because he's probably moving a good bit faster. Okay? In fact, let's just, guesstimate. Now he's going 14 meters per second. Okay? Now, he did not move an extra 9 meters per second. That's because the air resistance is pushing back on him. Okay, that net force is still Fg minus F air. Okay, and let's say the force of gravity was 200. Now the force of air resistance is bigger. Instead of being 20 like it was up here, maybe now it's 100. So now the net force is only 100 newtons down, which means his acceleration is much less. Okay, let's say maybe I don't know, -5 meters per second squared. Okay? Just making these numbers up. Right? And then 3 seconds later, he's still got the same gravity force as usual, same force of gravity. Okay? But now he's going at exactly the right speed that the force of gravity and the force of air resistance exactly match up. Now, he has accelerated from 14 meters per second. So let's just say you measure and he's going 15 meters per second down. Okay. Now, if you look at the F net, the net force, okay, at this point, the force of gravity we said was, let's say, 200 going down. If you look at the picture, the force of air resistance is exactly the same, but in the opposite direction. So that's 200. So 200 minus 200 is 0 newtons. If there is no net force, therefore, there is no acceleration. This is where the acceleration is 0 meters per second. This is where 15 meters per second will be the speed that he's going from here on out. And that's it. Okay? So to summarize, we have down here, let's get a good color, we have no net force. None. No net force here. The gravity and air are balanced out, which means that the forces are balanced. That's key. You might want to be writing this stuff down. Okay? The forces are balanced, which means they are in equilibrium. Equilibrium. Okay? Which means there is no acceleration Come on, fit that in. There we go. And lastly, this part right down here, this part where they're balanced, this is terminal velocity. Doesn't reach terminal velocity until those two forces are balanced out. That's terminal velocity. I hope it makes sense. If you have any questions, ask me in class.